Today we will be discussing epigenetics and how factors such as the environment, stress, behaviors, and social pressures can affect your gene expression. Now, exactly what is epigenetics? Epigenetics is the study of how your behaviors and environmental factors can alter gene function without changing the structure of your DNA.
Before we dive into the world of epigenetics, I first want to tell you how it changes your DNA. In every one of your cells is a long strand of code called DNA, a gigantic strand of ribosugars, bases, and phosphate groups that separates you from everyone else on Earth. Keeping this code tightly coiled together in the shape of a chromosome are millions upon millions of little proteins called histones. The amount of histone clumps DNA together is determined by the amount of acetyl groups present, a lot in their open and none in their clumped. When histones are tightly together, DNA can't be transcribed, and when DNA can't be transcribed, proteins can't be translated, meaning your cells can't express the gene in that area. Think of your DNA like a long road with words written on the asphalt, and heavy traffic is when your DNA is deacylated, aka when histones are clumped together. When this happens, you can't read the words on the road, just like the enzymes in your cells can't read that portion of DNA. Other ways that epigenetics occurs is through methylation, the adding of methyl groups to different parts of your DNA. These are called epigenetic markers because the presence of the methyl groups, 1 carbon and 3 hydrogens, can prevent transcription of your DNA just like the clumping of your histones. For these, you can think of them either as a bunch of stop and do not enter signs. So while the road, your DNA, is never changed, how we read the road and subsequently how we express the genes is.
Now let's shift gears to what causes these epigenetic changes. When scientists think about epigenetic factors, the first thing that usually comes to mind is environmental factors.
Environmental factors include 2 main categories: lifestyle choices and exposures. Lifestyle choices can include things such as what you eat and drink, as well as stress, sleep, physical activity, and substance use. Exposure can include things such as being exposed to chemical toxins in the form of pollutants, smoking, tobacco, and interacting with other chemicals found in consumer products.
Research has shown that these epigenetic factors can be the most influential during critical development periods of a child's life. Additionally, a mother's exposures and environmental factors can also lead to large epigenetic changes in a developing fetus. This is why doctors say you aren't allowed to smoke or drink when you're pregnant.
So we've talked about lifestyle choices, what you eat, how you exercise, whether you get enough sleep. But here's the thing, not everyone gets to make those choices freely. Your environment and social circumstances can actually force epigenetic changes on your body, whether you want them or not. Now, why could these epigenetic factors be a bad thing? Remember how Ashlyn explains that histone modifications and methylation are like traffic on a road or stop signs on your DNA? While certain environments and social factors can create permanent traffic jams or put up stop signs you never asked for, this can alter essential functions of your body.
Here's an example. Imagine you're a factory worker during the Industrial Revolution. You're 11 years old, working 12 hours a day, 6 days a week, and making about $1.25 a day. Your stress hormones, aka cortisol levels, are off the charts and you rarely get a good night's rest. You're constantly inhaling polluted air and smoke cigarettes like the rest of your coworkers. It's not your fault. You're young and just don't know any better and have a family to help and provide for. Now, what's happening in your body during this time? Let's take a look at your lung cells. Your lungs have special structures called alveoli. Alveoli are very tiny balloon-like air sacs where carbon dioxide and oxygen are exchanged between the air you inhale and exhale in your bloodstream. Now, these alveoli have what are called type 2 alveolar cells. These secrete a substance called surfactant. Surfactant is very important to your lungs because it reduces surface tension, allowing your lungs to inhale and exhale for you without sticking together. Keep in mind, if your lungs didn't have this substance constantly secreted from these cells, they would collapse on themselves.
When you're constantly inhaling polluted air and cigarette smoke, those type 2 alveolar cells are under attack. The toxic exposure triggers epigenetic changes, specifically methylation marks, that essentially turn off the genes responsible for making surfactant. Think about this. Your DNA still has the instructions. The genes are still there, but those methyl groups block the transcription factors from reading the gene. So even though your body knows how to make surfactant, the epigenetic factors have hijacked the system and stopped production. You may think this was over a century ago, but this exact process is still happening today, and it's being driven by the environments people are forced to work and live in. Chronic stress from poverty, discrimination, and unstable housing creates a constant traffic jam in your body's stress system. This activates what's called the HPA axis, your hypothalamic pituitary adrenal axis, and it stays activated long term. When this happens, your cortisol regulation gets completely thrown off balance. This is called cortisol dysregulation, and it's like your body's stress alarm never shuts off. This social stress doesn't just make you feel bad, it leaves actual methylation marks on your stress response genes, specifically on the glucocorticoid receptor promoter regions, the GR promoter. Remember Ashlyn's stop signs? Well, these methylation marks are stop signs placed directly on the very gene that's supposed to help your body clear the stress traffic. When it's silenced, your body gets stuck in a permanent gridlock of stress hormones. And here's what research from social epigenetics papers spanning from the 2010s all the way through 2024 have shown. Your socioeconomic status correlates with specific clusters of DNA methylation. We can literally map poverty and inequality at the molecular level in your cells. But here's the critical point. Systematic structures decide this exposure long before any individual choice is even possible. Look at historically redlined neighborhoods as a perfect example. By design, by policy, these communities have higher pollution, lower green space, more noise stress. Higher crime exposure, higher stress levels, eradication of community spaces, and the list goes on and on. Repeated policy cycles have reinforced these same toxic environments across generations. Unfair zoning laws and industrial siting, deliberately placing polluting factories and highways near low-income communities and communities of color, produce predictable health patterns that emerge decades later. The system creates the exposure, then blames the individuals for the outcome. Now add environmental toxins to this picture. Exposure to PM2.5, those tiny pollution particles, traffic emissions, and endocrine disruptors, chemicals that interfere with your hormones, triggers very specific epigenetic changes. First, hypermethylation of immune genes. This means your immune system genes get covered with too many methylation stop signs. They're being silenced precisely when you need them active to fight disease and inflammation. Second, hypomethylation of oncogenes. Oncogenes are genes that can cause cancer when they're turned on. Normally, you want methylation stop signs on these genes to keep them turned off and safe, but toxin exposure removes those protective stop signs, allowing dangerous cancer-related genes to become active. The combined result? This creates multiple pathways for dysregulated inflammation throughout your entire body. It's not just one traffic jam or one stop sign, it's a systematic shutdown of entire neighborhoods of genes, setting the stage for chronic disease. We've now seen how combined social stress and toxin exposure creates this perfect storm. And when industrial zoning and old infrastructure keep communities repeatedly facing the same exposures, these patterns compound generation after generation. But protective factors do exist. Consistent healthcare access, reliable transportation, real green space, social cohesion, and community stability, and reduced allostatic load through predictable and comfortable environments are protective factors that can actually reduce the biological wear and tear on your body. This isn't just about lungs. This epigenetic dysregulation is a direct pathway to the chronic illnesses that Risha will discuss, and it disproportionately impacts marginalized communities. The environment writes a dangerous story onto our cells, and epigenetics is the pen.
Now I'll be discussing the role of epigenetics in illness, injury, and chronic health. Certain factors, whether they are lifestyle choices or components of your environment, can result in changes to gene expression. As we've discussed, DNA methylation is one of these changes that can act as a stop sign in the road that is our DNA. When this occurs in genes that are responsible for regulating cholesterol and blood lipid levels, it can disrupt their normal function and result in an imbalance. This imbalance can contribute to the buildup of fatty deposits inside the arteries. Over time, these deposits can harden into plaque and narrow vessels. Narrowed vessels greatly increase your risk of cardiovascular disease. Illness and physical injury can also lead to long-term changes in gene expression. An infection or injury causes our body to send out inflammation signals. These signals can alter the chemical tags on our genes. Think of chemical tags as signs on the road, and yes, this includes our DNA methylating stop signs. When these alterations are short-term, they actually help us heal and recover. But what happens if these signs are up for too long? Increased inflammation for a long period of time can actually weaken our immune systems, making us more susceptible to chronic illnesses. Building on that, I'll now talk about how society perpetuates these outcomes, specifically among marginalized groups. As Laura discussed, factors that contribute to these changes are often not a matter of choice. Systemic inequalities continue to contribute to poor health outcomes among low-income communities and people of color. Take the Flint water crisis, for example. The contaminated water exposed primarily low-income and Black residents to lead, a chemical that can change DNA methylation patterns. As we have been discussing, this can have severe implications on health. This is a clear example of how systemic inequalities can contribute to long-term health disparities through epigenetics.
We've now seen how injuries, illness, and societal structures can create epigenetic damage. But what if this damage doesn't end with one person? Research by Yi and colleagues show that methylation patterns can persist across generations, but they emphasize context dependence. If parental stress loads were extreme, offspring don't begin at biological zero, they're already carrying some of their parents' epigenetic marks. Let me give you an example. Holocaust descendant studies show methylation differences in the FKBP5 gene and other stress-related loci. FKBP5 is a gene in the stress response pathway. Descendants of enslaved populations show similar stress-linked epigenetic profiles. These differences do not require a mutation, they simply reflect an altered gene expression pattern that got passed down for generations. Early life cortisol exposure reinforces these inherited stress phenotypes. If your mother or grandmother experienced extreme stress, the elevated cortisol in her body during pregnancy affected your development in the womb. The child may be born with a stress response system already primed for a hostile world. Then structural inequality keeps reactivating the same stress systems each generation, creating a vicious cycle. The pattern looks like this. Policies, which influence environments, which in turn influence stress, in turn epigenetic patterns, and then health disparities. And these health disparities that look inherited are in fact socially produced. Here's where timing becomes critical and where we find some hope. We can now measure accumulated biological damage with epigenetic clocks. These tools, developed by researchers like Horvath, Levine, and Newman in 2025, quantify biological aging acceleration. They show that chronic discrimination, instability, and trauma literally accelerate your epigenetic aging. You can be 30 years old chronologically, but 45 years old biologically. Epigenetic marks are plastic, not fixed. They can be changed. Remember, if the environment can put up stop signs, a better environment can take them down. Research shows that improving nutrition, safety, therapy, and reducing toxins leads to measurable epigenetic improvements. These health outcomes are not fixed in stone. By changing our environments and our policies, we aren't just changing lifestyles, we are healing biological legacies. We are rewriting the instructions for the next generation, offering a future where your zip code doesn't have to dictate your genetic destiny.